Hello everyone. This is my finals in Microprocessor. Let's pause for a moment and think about how amazing modern technology is. Every time you are watching a YouTube video, editing a photo, playing a video game, or even just sending a message, there is one thing working tirelessly behind the scenes: the CPU. The CPU, or the central processing unit, is the brain of your computer, smartphone, or even your smartwatch. But what exactly does it do? How does it take millions of lines of codes and turn it into the smooth, responsive experience we rely on daily? And how did we go from the CPUs, the size of entire rooms, to ones that now fit in the palm of your hand? So in this video, we are going to explore how CPUs work, breaking down their components and processes, the incredible evolution of CPUs from the Intel 4004, the first microprocessor, to the multi-core AI-powered processors we use today. We will also see practical examples, discuss milestones in CPU history, and explore the impact of these advancements on technology and society. By the end, you will not only understand how CPUs work, but also appreciate how they have shaped the modern world. So let's see. So what is a CPU? The CPU, or the central processing unit, is often referred to as the brain of the computer. But what does that really mean? At its core, the CPU is responsible for executing instructions. Think of it as a highly efficient worker on an assembly line, performing tasks one after the other at incredible speeds. For example, when you open a website, the CPU processes the code that tells your browser how to display the text, images, and the layout. It's the CPU that makes everything happen, from small tasks like moving your mouse cursor to complex calculations like rendering 3D graphics. But the CPU doesn't work alone. It relies on other components. The RAM, or the random access memory, this is like the CPU's desk. It's where the CPU temporarily stores data it's actively working on. The storage, your SSD or hard drive, is like a filing cabinet holding all your files and programs. When you open something, the CPU fetches it from storage and places it into the RAM. The third one is the peripherals. Devices like your keyboard, your mouse, or the monitor send input to the CPU, which processes that data and sends the output back to the appropriate device. So inside the CPU, the key components. Now let's take a look inside the CPU itself. There are three main components you need to know about. The arithmetic logic unit is the first one, or the ALU. This is where all the calculations happen. Whether it's adding numbers, performing logic comparisons, or even deciding what task to prioritize, the ALU handles it all. For example, if you are gaming, the ALU calculates your character's position as you move. Next one is a control unit. The control unit acts like the CPU's manager. It fetches instructions from memory, decodes them, and tells the ALU and other components what to do. Think of it as a conductor of an orchestra, ensuring every part of the CPU works in harmony. Third one is the registers. These are small, ultra-fast storage locations within the CPU. They hold data and instructions that the CPU is actively working on. For example, when the CPU is adding two numbers, those numbers are stored in registers for quick access. Imagine a calculator. When you type in 5 plus 7, the numbers go into the registers, then the ALU performs the addition, and the result will be stored back in a register or sent to memory. The fetch, decode, and the execute cycle. Every task the CPU performs follows a simple yet powerful process called the fetch, decode, execute cycle. This cycle happens billions of times per second, enabling the CPU to handle everything from basic math to running complex programs. So here's how it works. Fetch, the CPU retrieves an instruction from memory. Decode, it translates the instructions into signals it can understand. Execute, finally, it carries out a command, whether that's adding numbers, storing data, or sending output to a device. For example, when you type on your keyboard, the CPU fetches the keystroke input, decodes it to determine the corresponding letter, and then executes the instruction to display that letter on your screen. Let's say you are playing a guessing game on your computer. When you enter a number, the CPU fetches that input, compares it to the target number, and outputs whether it's too high, too low, or correct, all in microseconds. The clock speed and the synchronization. Another important concept is clock speed, measured in gigahertz or the GHz. This tells us how many cycles the CPU can complete per second. A CPU with a clock speed of 3 GHz can handle 3 billion cycles per second, but speed isn't the only factor. The CPU also relies on synchronization, much like a conductor keeping an orchestra in time. The CPU's clock ensures that all components work together harmoniously, preventing errors or delays. Think of clock speed as the drum beat of a band. Faster beats mean the band plays quicker, but if the beat is inconsistent, the music falls apart. Similarly, the CPU look ensures all operations are synchronized. The evolution of the CPU. The Intel 4004 or the birth of microprocessors. Our journey begins in 1971 with the Intel 4004, the first commercially available microprocessor. It had just 2,300 transistors and could perform 92,500 instructions per second. While that might seem tiny by today's standards, it was revolutionary at that time. Before the 4004, computers were massive machines, often filling entire rooms. The 404 changed everything, packing all that processing power into a single chip. It was first used in calculators, but it paved the way for personal computing. Imagine a world without laptops or smartphones. The Intel 4004 was the first step toward making modern devices possible. The Intel 8086 and the x86 legacy. In 1978, Intel introduced the 8086, which gave us the x86 architecture, a design that's still used in the modern CPUs. This processor introduced features like segmented memory, allowing it to handle larger datasets more efficiently. The 8086 powered the first IBM PCs, which marked the beginning of the personal computing revolution. Suddenly, computers weren't just for businesses or research labs, they were for everyone. The multitasking revolution, the 1980s. The 1980s brought multitasking to the forefront. CPUs like the Intel 8286 introduced protected memory, enabling multiple programs to run simultaneously without crashing. This was also the era when graphical user interfaces or GUIs became popular, thanks to systems like the Apple Macintosh. Imagine browsing the web while listening to music and editing a document. That's multitasking, and it became possible because of advancements in CPU design. The 1990s or the modern architectures. The 1990s saw the rise of 32-bit architecture with processors like the Intel 8386. These CPUs introduced features like pipelining, where multiple instructions could be processed simultaneously, and caching, which sped up memory access. These advancements laid the foundation for today's multi-core processors, which handles complex tasks like AI and gaming with ease. So the introduction to GPUs and the sub one, the bridging complexity and simplicity. So today we are diving into two fascinating topics: the powerful GPUs that drive our digital world and the sub one architecture, a model of simplicity that forms the bedrock of computing. Every advanced system we use today has its roots in fundamental principles. GPUs represent the cutting edge of computation, capable of running immersive games, training AI, and analyzing vast datasets. On the other hand, the SAP1 is a simplified educational model that demonstrates how computers function at their core. Why are we addressing these two together? Because understanding simplicity helps us appreciate complexity. By the end of this video, you will know how computers evolved from basic architectures like SAP1 to the sophisticated GPUs we use today. Think of this as a comparing a modern spacecraft to the first airplane. Both fly, but the technology has advanced exponentially, so let's explore this journey together. The birth of GPUs, a historical perspective. Graphics processing units, or the GPUs, weren't always the sophisticated devices we know today. Their story begins in the 1980s during the rise of arcade games like Space Invaders. Early graphic chips such as the TMS 9918 could render simple 2D visuals. Fast forward to the 1990s and GPUs began supporting 3D rendering. NVIDIA's release of the GeForce 256 in 1999 was a game changer. It was marketed as the world's first GPU, introducing hardware transformation and lighting. Suddenly, games like Quake 3 Arena became more immersive, with smoother graphics and realistic lighting effects. Imagine playing a pixelated arcade game versus exploring a beautifully rendered 3D world. The leap in technology was transformative, setting the stage for the GPUs we rely on today. The modern GPUs, a deep dive into the architecture. Today's GPUs like NVIDIA's RTX 4090 or AMD Radeon RX 7900 are technological marvels. So let's break down their architecture. CUDA cores. These handle general computations in parallel tasks. For instance, when rendering graphics, each core processes a small part of the image. The tensor cores. These specialize in AI tasks. They handle the matrix operations critical for training and running neural networks. Third one is the ray tracing cores. These simulate how light interacts with objects, creating stunningly realistic graphics in games and films. To put things into perspective, the RTX 4090 has over 16,000 CUDA cores. That's like having 16,000 workers processing tasks simultaneously. Think of a GPU as a giant orchestra. CUDA cores are the musicians playing their parts. Tensor cores are the specialists handling complex solos, and ray tracing cores are the lighting team creating the stage ambience. The real-world applications of GPUs. GPUs aren't just for gaming. They power a wide range of industries. Gaming. First one is the gaming. GPUs render 3D graphics in real time, delivering lifelike experiences. Second one is the artificial intelligence or the AI. GPUs accelerate AI training and inference, powering applications like self-driving cars and virtual assistants. Third one is the scientific research. From simulating protein folding to predicting weather patterns, GPUs enable complex computations. Fourth one is the finance. High frequency trading relies on GPUs to analyze the market trends and to execute trades in milliseconds. The last one is the cryptocurrency mining. GPUs solve cryptographic puzzles to validate the blockchain transactions. For example, Google's AI systems rely on GPUs to process massive datasets, enabling real-time language translation and image recognition. Without the GPUs, such advancements would take much longer. GPUs and AI, the driving the future of intelligence. Now let's explore how GPUs are shaping the future of artificial intelligence. GPUs excel at parallel processing, which is critical for AI tasks like training neural networks. For example, consider an image recognition AI. The GPU processes thousands of pixels simultaneously, analyzing features like edges, colors, and patterns to identify objects. This capability cuts down the processing time from days to hours. Tensor cores in modern GPUs, such as NVIDIA's RTX series, are specifically designed for AI tasks. They handle matrix multiplications, a key operation in machine learning, more efficiently than traditional cores. This makes GPUs indispensable for tasks like natural language processing, real-time translation, and autonomous vehicles. Looking ahead, GPUs will continue to play a central role in AI advancement, powering breakthroughs in areas like medical diagnostics, predictive analytics, and robotics. Think of GPU as the engines of the AI revolution. Without their speed and efficiency, many of the AI applications we take for granted wouldn't be possible. The GPU memory and parallel processing. Modern GPUs rely on high-speed memory like the GDDR6X to keep up with their processing power. This memory ensures that data can be fed to the GPU cores without delays, which is critical for rendering high-resolution graphics or processing AI algorithms. GPUs also use SIMD, the single instruction multiple data architecture. This allows them to execute the same operation across multiple data points simultaneously. For instance, when rendering a 4K video, each pixel is processed in parallel, drastically reducing the time required. Imagine a painting working on 100 canvases at once versus one canvas at a time. SIMD enables GPUs to handle thousands of operations simultaneously, making them incredibly efficient. So now let's go to sub 1. So, let's step back in time to explore the sub 1, or simple as possible one computer. This is a basic computer architecture designed for educational purposes. It strips down the complexity of the modern system to reveal the core components of a computer. Sub 1 includes program counter or PC. It tracks down the memory address of the next instruction. Next one is the instruction register or the IR. It stores the current instruction. Next one is the accumulator or the ACC. It temporarily holds arithmetic results. Next one is the RAM. It stores both data and instructions. Think of SAP 1 as a one-room house with all the essentials, a bed, a table, and a chair. It's simple but functional, and it helps us understand the basics of how computers work. Now, again, the fetch, decode, execute cycle in SAP 1. SAP 1 also operates using the fetch, decode, execute cycle, the backbone of all computing. Fetch, the program counter, points to the memory address of the instruction, which is fetched and stored in the instruction register. Decode, the control unit, interprets the instruction. Then the execute is the operation is carried out such as loading data, adding values or halting the program. This cycle might seem simple, but it's the same process used in modern computers, just scaled up. Every application you run, whether it's a web browser or a game, relies on this cycle. Programming in SAP 1. Getting hands-on with assembly language. Programming SAP 1 involves writing in assembly language, a low-level language that directly interacts with the hardware. So let's try it a simple program to add two numbers. LDA01. It loads the value at memory address 01 into the accumulator. Add 02. It adds the value at the memory address 2. STA03. It stores the result at memory address 3. HLT is to halt the program. Each instruction corresponds to a specific operation, making assembly language both powerful and precise. It's like giving step-by-step instructions to a robot. While it requires more effort than high-level languages, it offers complete control over the computer's behavior. So deep dive into the SAP 1, the instruction set and the memory addressing. So let's take a closer look at the instruction set and memory addressing in SAP 1. The SAP1 instruction set consists of basic commands like the LDA, load accumulator, add or the add, sub or the subtract, and HLT, the halt. Each instruction corresponds to a unique binary opcode, which the control unit decodes and executes. For example, LDA01 means load the value at memory address 01 into the accumulator. Add 02 means add the value memory address 02 to the accumulator. Memory addressing is equally fascinating. SAP1 uses a simple RAM module to store both data and instructions. Each memory location has a unique address, allowing the program counter to fetch the correct instruction sequentially. The beauty of SAP1 lies in its simplicity. Even though it's a basic model, it demonstrates key principles like opcode, decoding, and memory management that are used in every modern computer. Imagine SAP1 as a small library with labeled shelves. Each shelf holds a specific piece of information, and the librarian, the program counter, knows exactly where to fetch it. This method ensures that every operation runs smoothly and efficiently. So SAP 1 in today's world. Why we need to study the SAP 1? Because its principles are foundational to all modern computing. Concepts like memory addressing, the fetch decode execute cycle, and instruction sets are still used today. Understanding this basic is essential for anyone pursuing a career in computer science or engineering. Think of SAP 1 as the alphabet of computing. Without it, you can form words, sentences, or entire systems. It's the starting points it's the starting point for understanding how technology works. So, in conclusion, we need to link the past and the future. So, what we have learned CPUs are the heart and brain of the modern technology, transforming instructions into the seamless experiences we enjoy daily. The revolution from the Intel 4004 to today's advanced processors has been nothing short of extraordinary. But CPUs aren't the only stars in the world of computing. GPUs, with their incredible parallel processing power, have emerged as the muscle of the modern technology. They are transforming industries from gaming to artificial intelligence by handling trillions of calculations per second. Think about it. GPUs bring lifelike visuals to video games, accelerate AI training, and power scientific simulations, all by applying the same fundamental principles of instruction execution. And let's not forget where it all started. With models like the SAP1, this simple architecture reminds us of the elegance of the computing's foundation. The same fetch, decode, execute cycle that drives SAP1 is scaled up and optimized in CPUs and GPUs. Without these basic building blocks, the technological marvels we rely on today wouldn't exist. The story doesn't end here. With AI, quantum computing, and neural processing units on the horizon, the future of computing promises to be even more exciting. Imagine GPUs optimized for AI on quantum scale, or CPUs and SAP1 principles blending into entirely new architectures. Who knows what the next decade will bring? What's clear is that the understanding the past, from SAP1 to the Intel 4004, helps us appreciate the present and prepares us for a future fulfilled with limitless possibilities. Remember that technology is a journey, and by understanding its roots, we can better navigate its future. Whether you are a gamer, programmer, or just curious, I hope this video has inspired you to explore further. Thank you.